Hello everyone, this is Dr. Dhiman and I welcome you all to this tutorial series in class 11 physics. I am following the book NCERT textbook. I am following the physics book part 1. So in this video we will learn about the dimensions of physical quantities. So for that physical quantity, suppose temperature or intensity or length or mass or time, these are the some quantities or some measurements. So for these measurements we will have some dimension. So we can define the nature of physical quantity by its dimension. That means after looking at the dimension we can easily understand what type of physical quantity is that one. So we have 7 basic quantities through which we can represent all the other quantities and we can derive in terms of some combination. So first of all, let us see what is a dimension. Okay, it is the nature of the physical quantity by which we can represent it in an understandable format. So there are 7 base quantities. Most widely used or most commonly used are the length, mass and time. Okay, so let me write down one by one. So first one is length. Length is nothing but it is the distance between some 2 points. So if we measure this distance, then it is called as the length. If we have a rod, then if we measure the length, then it will be in suppose meter unit. A length is represented as capital L within square brackets. This square bracket represents that we are dealing with the dimension of the quantity. That means if we are represented in this form, that is capital L with a square bracket, this square bracket represents the dimension of the quantity. Similarly, we have 6 other quantities. Second one is the mass, and we represent it in dimension as capital M within square bracket. And third one is here we have capital T within square bracket. This is the third one. Fourth basic quantity is suppose electric current. In case of electric current, the dimension is represented as capital A within square bracket. The fifth one is thermodynamic temperature. Thermodynamic temperature is represented in dimension as, so the SI unit is Kelvin, so capital K within square bracket. This is the thermodynamic temperature. And the sixth one is the luminous intensity, that is the intensity of light. Unit is candela. Okay, so in case of luminous intensity, we have a dimension of small c small d within square bracket. Okay, this is the dimension of luminous intensity. This square bracket, when you use, this means the dimension. So this CD is nothing but the candela, the unit. The last basic quantity is the amount of substance. So amount of substance is represented in mole. Okay, the unit is mole and the short form is small m o small l. So within square bracket, if we write, then this is the dimension of the amount of substance. So this square bracket represents we are considering the dimension of the quantity. Okay, that's the dimension of a quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. So the definition of dimension, you can call it as, so the dimension of a quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We will see one by one. These are the 3 dimensions that are most widely used in the mechanics, and all the other units we can represent it with these 3 dimensions. We have seen about all the 7 base quantities that are used for the representing the dimension. Suppose we have a cube like this. So this is suppose the cube, and the length is suppose small l, the breadth is small b, and the height is small h. Okay, this is one suppose cube. So in this cube, what we can write, the volume, if we want to find out the volume, we have to multiply the length with breadth with height. So here the volume of this cube is equal to length into breadth into height. So these are the 3 quantities. So if we represent with these 3 with dimension, what will have? Length has a dimension capital L within square bracket. This b is also a length. Okay, it is, the value might be different, the magnitude might be different, but the dimension is similar. So this is capital L, and for the height also it is a length. So here also we have capital L. So for the volume, the dimension is here the capital L cube within square bracket. Okay, so this is the dimension of this volume of this cube. let us see some other examples. Suppose if we want to consider, so if we represent this volume in case of, suppose using some dimensional equation form, then we can write it as capital V. Capital V represents the volume is equal to m to the power 0 L cube and t to the power 0, okay, within square bracket. So this is the dimensional equation, or we can write it to be simply L cube. You need not to write this m to the power 0 or t to the power 0. So in this way we can represent it. Similarly, if we want to find out the dimension for force, so first of all we have to understand what is force. Force is the mass into acceleration, F equal to ma as per the Newton's second law. So F equal to ma, that is mass into acceleration. So mass into acceleration, this is the force definition. So mass means the dimension is capital M, and acceleration means change in velocity per second. So the acceleration has a unit of meter per second square. So considering this unit, we have to see the dimensions. So this meter has a dimension of capital L, and here suppose time, so here we have per second square, that means we will have here to the power minus 2. So this is the dimension, or we can write it simply as m into L into t to the power minus 2. Okay, so this is the dimension of this force. So keep in mind that in case of dimensions, magnitudes are not considered. So whatever be the magnitude, you just ignore it. If you are asked to find out the dimension of any physical quantity, then you have to represent in this type of form. Okay, so in this way you can represent any type of quantity. Now let us see the velocity. So in case of velocity, what is the definition of velocity? So velocity is displacement divided by time. So if we want to write the dimension now, the displacement means it is a distance or it is a length. So here we have capital L. Time has a dimension of capital T, that means capital L divided by capital T within square bracket. So we can write simply as this t is in denominator, we can write in t to the power minus 1. Okay, so here we can write L t to the power minus 1. So this is the dimension of this velocity. Velocity is represented in small v. This is the dimensional equation. If you are asked to find out the dimensional equation of velocity, then this is the dimensional equation, or we can say that this is the dimensional formula for velocity. Therefore, an equation obtained by equating a physical quantity with its dimensional formula, it is called as the dimensional equation of the physical quantity. So let us consider some other dimensional equations I am writing here. Okay, so let us consider some other equations. So we have already seen about volume. In case of volume, so for volume the dimensional equation will be small v. No, volume is represented in capital V. So here we can write capital V is equal to, so in case of volume we have L cube, or we can write it as m to the power 0 L cube t to the power 0, or we can directly write L cube within square bracket. Similarly for now velocity, in case of velocity what we have, velocity is meter per second. So looking at the unit of that quantity, physical quantity, so looking at the unit you can directly find out the dimension. So meter per second means, meter means it is the L, and second means it is the time capital T. So we can write it as this velocity is represented in small v. Okay, small v is equal to, this is m to the power 0 L into t to the power minus 1. So this is the dimensional formula, or this is the dimensional equation for velocity. Similarly, now let us see about the force. So force has a dimensional equation of, suppose here we have capital F, it is this capital F represents the force. So what is the force? We have already obtained m into L to the power t to the power minus 2. So m L t to the power minus 2. So you can write it to be 1 t to the power minus 2. Okay, so if you do not write this power once also, then it is understood that we have a 1 here. Similarly, suppose now we consider the mass density. So what is the mass density? Density is represented with rho. So rho within square bracket, what is the density? It is the mass per unit volume. Okay, so mass has a unit of capital M, and per unit volume has a unit of L cube. Per volume means it is L to the power minus 3. You can easily find out this, and T to the power 0. Okay, so this is the dimensional equation for mass density. Therefore, the dimension of mass density can be expressed as, now if we want to analyze this mass density, so what we can say, we have 1 dimension of mass minus 3 dimension of length and 0 dimension of time. So let me write down here. Now if we want to find out some other quantities, suppose the acceleration, pressure, work, let us see one by one. So what is acceleration? Acceleration is the change in velocity per unit time, or the change in velocity divided by change in time. So acceleration is usually represented with small a. So it is the change in velocity divided by change in time. Here we will have, this is the velocity means small v, and the time is capital T. The velocity is meter per second. So meter is the unit of length and second is unit of time. So in this way we will have L T to the power minus 1, and this T is nothing but capital T only. So if we take this denominator T to the numerator, then here we will have L into T to the power minus 2. So here we can write A is equal to L T to the power minus 2. Okay, so this is the dimensional equation of acceleration. Now let us see about the pressure, capital P. So what we'll have, pressure is the force per unit area. So we can write it as force per unit area. So force per unit area is the pressure. So force has a unit of ml T to the power minus 2. ml T to the power minus 2. And then we have L square. So this pressure will have a dimensional equation P within square bracket is equal to, so here we'll have m L to the power minus 1 T to the power minus 2. This is the dimensional equation for pressure. Now let us see for work. So work can be expressed also in case of, suppose energy also has the same unit, work done also expressed in joule, and energy is also expressed in joule. So in case of work and energy, we will have the same dimensional formula. Suppose let us find out for the work. Work done is usually represented with capital W. So in case of capital W, the work is the force into displacement. Force into displacement is the work done. So in case of force, dimension is ml T to the power minus 2. So force has a unit of Newton, and Newton, if we break into some basic quantity, basic units, then we have kilogram into meter per second square. So kilogram is the SI unit of mass, meter is the SI unit of length, and second square, per second square means it is T to the power minus 2. In this way you can use some shortcut. So if you know the unit of that quantity, then you can directly write down the dimension of that quantity. Again we have the displacement. So this displacement has a dimension of meter, or we can write it to be L. So we have already L here, so it will be m L square T to the power minus 2. So this will be the dimension of work done. So this work done dimension will be similar to the energy dimension. Now let us consider some example. Now let us consider the example number 2.15. Let us consider an equation that is half of mv square is equal to mgh. Small v is the velocity, g is the acceleration due to gravity, small m is the mass. Okay, where m is the mass of the body, small v is velocity, small g is the acceleration due to gravity, and small h is the height. Okay, check whether this equation is dimensionally correct or not. So here we are given half of mv square is equal to mgh. So in the left hand side we have half of mv square. We can neglect this quantity because this half is the constant. Now let us see the dimension of this left hand side. So here we can write dimension of left hand side of the equation. So half of mv square, half we can neglect. Now let us see, this small m has a dimension of capital M within square bracket. This small v, it has a dimension of, that is the unit is meter per second. So it will have a dimension of L t to the power minus 1. We have already seen this one. So here we'll have a square because mv square is there. Okay, so here we can write this capital M, and here we can write L square t to the power minus 2. So if we combine this, we'll have M L square t to the power minus 2. So this is the dimension from the left hand side of this equation. Okay, now let us see the right hand side dimension. In the right hand side we have mgh. M has a dimension of capital M within square bracket. G is nothing but it is the gravitational acceleration. So what we can write, acceleration means meter per second square. So meter has a dimension of length, and per second square means t to the power minus 2. So mg into h. So h is nothing but a distance. Small h is the height. Okay, or we can say that it is a length. So here we'll have capital L. M L square t to the power minus 2. Okay, so from the left hand side and the right hand side we can see that these two dimensions are the same. Here we can see this dimension and this dimension is exactly same. So we can say that this equation is dimensionally correct. So we can write this much for today. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Do not forget to share this video with as much of your friends. Thank you.